Hello students, welcome to EPG Pathshala Biophysics. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences, West Bengal University of Technology. Formerly, I was Professor and Head, Biophysics Division, Shah Institute of Nuclear Physics in Kolkata. Today, we will talk about harmonic and Morse oscillators and the energy levels for molecular vibrations. Name of the paper, as you all know, is Quantum Biophysics. Now, what are we going to learn from this lecture? Well, these are solutions for energy levels and wave functions, probability distributions for harmonic oscillator, the energy levels of a vibrating molecule, and finally, Morse oscillator, a model for real vibrating molecule. The Bohr model tells us that the electrons have discrete energy levels in an atom. In diatomic molecules like H2 or HCl, the electrons have discrete energy levels that are different from those in atoms. These energy levels can be obtained from molecular orbital theory, about which we'll learn later. But for the time being, let us understand that a diatomic molecule, unlike an atom, has additional degrees of freedom like vibration and rotation. Since the tiny molecules are governed by the laws of quantum mechanics, these can vibrate or rotate only with discrete energy levels. In this lecture, we study the vibrational energy levels of a molecule by relating these to the energy levels of a quantum mechanical oscillator. We shall see that molecular vibrations are not exactly simple harmonic. These can be treated as anharmonic Morse oscillators. Let us now come to the objectives of this lecture. The Schrödinger equation is solved for harmonic oscillator to obtain the discrete set of energy levels and wave functions. Lowest level gives the 0-point energy. It is found that there is always a probability of observing the oscillator outside its classical domain. Energy levels of a vibrating molecule are the same as those of an oscillator having reduced mass of the molecule. The vibration of a molecule in real life is anharmonic, and its energy levels are best obtained on the basis of Morse potential. Let us come to the topics one by one. First of all, let us define a harmonic oscillator. A ball attached to the end of a spring makes a harmonic oscillator. On stretching, the restoring force F is proportional to the displacement of the particle from its resting position, which is x equal to 0, and acts opposite to the direction of stretching. If the mass of the particle is m and force constant of the spring is k, then the restoring force equal to mass times the acceleration. Well, that's the definition of force, and this is proportional to x, and since this is the restoring force which acts in the opposite direction, so you have to put a minus sign. So the force is equal to the restoring force is equal to minus kx. This basically defines the harmonic oscillator. Now, in terms of the angular frequency, well, this gives the equation d square x dt square plus omega square x equal to 0, where omega is root k by m, or k is equal to m omega square. So in this equation, k is called the stretching constant or the force constant of the spring, as already mentioned, and omega is the angular frequency. So from our knowledge of waves and oscillations, the time period of the oscillator is t is equal to 2 pi upon omega equal to 1 by nu 0. The frequency of oscillation nu 0 fixed by k and m is an intrinsic property of the oscillator, because k is the spring constant and m is the mass of the ball. So these two parameters fix nu 0. So
This is an intrinsic property of the oscillator. The solution is of the form x equal to a sine omega t plus b cosine omega t, well, as we already know from our school physics. Now here we are interested in figuring out the potential, you see, by using the formula force equal to minus dv dx. This is the usual formula which is mostly valid when you want to calculate potential using the force or the force using the potential. So here in this case we know the force. We have already defined the force, which is equal to minus kx, and therefore we have to find the potential, and this potential is needed for Schrodinger equation. So the potential from the first equation, the potential is equal to minus integral of fx dx. And remembering fx is equal to minus kx equal to minus m omega square x, vx becomes, on integrating, half kx square or half m omega square x square. Now this is the equation of a parabola passing through x equal to 0. Thus Vx represents a parabolic potential well for the harmonic oscillator, for which Schrodinger equation should be solved. So this parabolic potential well is shown later. Well, this represents a parabola, as I said. The total energy E of the harmonic oscillator at any time is the sum of its kinetic and potential energies. At the turning point, that is x equal to a, the kinetic energy is 0 and the total energy is equal to the potential energy. Since the total energy is conserved, therefore p square upon 2m plus half m omega square x squared, that is the kinetic and potential energies, the sum of the two, is equal to the potential energy when the bob is at the end of its vibration. Then the displacement is equal to the maximum displacement, which is the amplitude. So this can be equated to half m omega square a square. Now a classical oscillator can have any amplitude a, and so it can oscillate with any energy E. The situation is different in the world of atoms and molecules, where classical laws no longer operate. In quantum mechanics, the harmonic oscillator vibrates with discrete energy levels only. It absorbs or emits light for transition from one energy level to another. There is always a very small probability of observing the oscillating particle outside its classical amplitude. Now, a few other unusual features follow. Well, this will be described after the Schrodinger equation is solved for the oscillator. So let us write down the Schrodinger equation. For the potential, we have replaced V by half m omega square x square. So the second equation is the Schrodinger equation for a harmonic potential. Introducing dimensionless variable y and epsilon for the position and energy of the oscillator. Well, this is just for convenience that we introduce these variables y and epsilon, which are written on the screen. So omega is root alpha times x, and epsilon is 2e upon h cross omega. These are dimensionless quantities, and alpha is m omega upon h cross. So in terms of these dimensionless variables, Schrodinger equation becomes d square psi dy square plus epsilon minus y square psi equal to 0. Now, to solve this equation, we first look for an asymptotic solution. For y tending to infinity, or x tending to infinity, which means which are the same, this equation assumes the form d square psi dy square minus y square psi is equal to 0. The asymptotic solution is psi y equal to e to the power plus minus y square upon 2. Only negative sign is acceptable so that the wave function does not blow off for y tending to infinity. The general solution is assumed to be psi equal to some function of y times the asymptotic solution, which is exponential minus y square upon 2. So differentiating this twice and plugging the result in Schrodinger equation, it is easy to check that the function hy satisfies the differential equation d square h dy square minus 2y dh dy plus epsilon minus y h equal to 0. Comparing this with the standard Hermite equation, we find that the function hy is identified as a series of Hermite polynomials provided epsilon minus 1 is equal to 2n. So this condition gives the discrete values en equal to 2n plus 1, where n is equal to 0, 1, 2, and so on. And since epsilon n is connected to the energy levels, so we get En equal to n plus half h cross omega, or which can also be written as n plus half h nu 0. The normalized wave functions are written at the bottom of the screen, and this normalization factor is obtained by using known mathematical properties of the Hermite polynomials. So you can get the energy levels, which E0 equal to half h cross omega, half h nu 0. If you put n equal to 0, this is the energy for the ground state, and this is called the 0-point energy. This doesn't have any classical analog, because a classical oscillator, you see, can the minimum energy of vibration is 0 when the oscillator is at rest. But in quantum mechanics, a quantum mechanical oscillator has always a minimum energy or a residual energy, which is half h cross omega or half h nu 0. Well, this is contrary to the expectation of classical mechanics, and this ground state energy is referred to the 0-point energy. So this is very important to note. And then you have the higher levels of energy, the E1, E2, and E3, which are given by 3 by 2 h nu 0, 5 by 2 h nu 0, or 7 by 2 h nu 0. So you can see that the energy levels are equally spaced, and the difference between any two levels is just h nu 0 or h cross omega. So I told you how to find out the normalization factors. You see, you can find out the corresponding wave functions, that is corresponding to 0-point energy. You have the wave function psi 0, which is written on the screen, and then the subsequent wave functions are psi 1, psi 2, and psi 3, which also you can see on the screen. Now this figure is important. Well, this is actually the plot of the square of the wave functions. The square of the wave functions, as you know, gives us the probabilities. These are the probability functions, and we are interested in looking into the nature of the probability functions. So you can see these figures, which are very important. Actually, I was referring to the parabolic potential well, because this is the form of the potential well, see, when it is represented pictorially. So you have the parabola, and then you have the energy levels. The 0-point energy is half h nu 0, and then you have the first level of energy, this 3 by 2 h nu 0, 5 by 2 h nu 0, 7 by 2 h nu 0, and so on, so that the energy gap between any two successive energy levels, well, is h nu 0. So this is one important point to note, that the energy levels are equally spaced and you have a 0-point energy. And the second point is about the wave function or the probability functions, as a wave function squared. So if you plot them, you will have, they will look like this, that, well, this is the probability function for the ground state. Well, this just got one bump, and this is the probability function for the first excited states, which corresponds to n equal to 1 and 2 humps. And then this is the probability function for n equal to 2. So it has got 3 humps. Well, all the humps are not equal. Okay, the humps at the corner, they are sort of more height. And then you have the next higher level, where the probability function will look like this, and so on. It will go on like this. And finally, when you this is n equal to 3, but supposing you plot the same probability function for n equal to 10, then what do you get? Then you get a probability curve like this. Okay, the feature is the same. Well, you have got multiple bumps, and the bumps, the heights of these bumps are more than the heights of the bumps towards the center. So it will the probability function will look like this. Now, there are a few important things to note. Number one, as I already mentioned, that see, there is always a small but finite probability of observing the quantum mechanical oscillator outside its classical amplitude. So the classical amplitudes are marked here. That this is A1, the next one is A2, the next one would be A3. So I have just shown this amplitude A1, and here the amplitude is A10. So in all these cases, well, we find that there is always a small but finite probability of observing the oscillator outside its classical domain or outside its classical amplitude. So this is one important point to note. The other important point to note is that, especially talk about the probability function for the ground state, and it looks like this. But you see, in the case of an oscillation, let us take the case of the oscillator which we are considering, or a pendulum. You see, a pendulum spends more time at the end and it passes through its middle very fast. Well, the same happens for the case of the ball at the end of a spring. When you disturb the spring, well, the probability of observing the ball at the ends is more than the probability of observing the ball in the middle, because it spends more time towards the end. It stops at the ends and comes back and passes very quickly to the middle, through the middle. So we would expect the probability distribution to be the other way around. That is, it should be minimum at x equal to 0 and more towards the end. But here you find that the situation is just the reverse. So this is, well, one tends to think that this is perhaps not right. But actually there are enough evidence that this is exactly what happens for a quantum mechanical oscillator. Well, when the molecules oscillate, okay, the oscillation of molecules can be related to quantum mechanical oscillator. So then this is exactly what happens. So this is not something which is wrong because it doesn't agree with our classical ideas. To see this very clearly, see, what we find is that when you go to higher state, well, sufficiently higher state like n equal to 10, as we have shown here, you have multiple bumps here. But if you take the average, well, the dotted line or the dashed line shows the average of these bumps. So we find that the average probability curve, see, that matches with our expectations according to classical mechanics, right? Well, here you find that we were confused because we found that the probability was maximum at x equal to 0, but when you go to a higher state like n equal to 10, then you find that the average probability curve has a minimum at x equal to 0. So this is something which agrees with what we would expect from classical mechanics. So what we are doing, these are not wrong, because this is called correspondence principle, that when you go to a higher quantum mechanical state, then the average quantities, they appear to look like what you see in classical mechanics. Okay, so this is not really contradiction, but these are just facts. Well, let me tell you how to find out the amplitudes, because in the diagrams we had shown the amplitude. So you see from this equation, well, if you equate this oscillator energy levels, the classical expression, we have found out the oscillator energy levels, n plus half h cross omega. So if you equate this to this, then you get A0, that is h cross by m omega, and An, that is the amplitude. This is the classical amplitude for the nth state. So that is equal to n plus 1 h cross by m omega under the root, which is equal to n plus 1 half A0. Now the oscillator can be observed, as I already said, that the oscillator can be observed outside its classical domain with small probability. And the nature of the ground state probability function appears abnormal, though it is correct. Average behavior for large values n agrees with classical result. And finally, the dimensionless variables Y and E can be expressed in terms of the ground state parameters, and you get this. So actually what you defined Y is the ratio of X and A0, and what you have defined epsilon is the ratio of E and E0. A0 and E0, these are ground state parameters.
Let us now ask this question. Is it possible to relate the vibrational energy levels of a diatomic molecule like oxygen, hydrogen, or HCl to those of a harmonic oscillator? The answer is yes, if the mass of the oscillator is replaced by what is known as reduced mass of the molecule. Now the question is, what is reduced mass of the molecule? We shall define this very soon, and you will be able to see this on the screen. And finally, this is not enough, as the molecular vibrations are not exactly simple harmonic. A molecule can be best represented by an harmonic Morse oscillator. So we will study what is an harmonic Morse oscillator and what are the energy levels of such an oscillator, and then we'll relate these to the energy levels of a diatomic molecule.
Now we talk about molecular vibrations. A harmonic oscillator consists of a single mass at the end of a spring, while a vibrating diatomic molecule has two atoms of masses m1 and m2 at the ends of a spring-like chemical bond. So according to results of classical mechanics, an oscillator can serve as a suitable model for vibrating molecule, provided we fix the mass of the oscillator equal to the reduced mass mu of the molecule, where 1 by mu is equal to 1 by m1 plus 1 by m2. So m1 and m2 are the two masses of a diatomic molecule. Supposing it is a hydrogen molecule, then m1 and m2, they are the same, equal to the hydrogen, the mass of the hydrogen atom. So this is the reduced mass of this is how the reduced mass of a molecule is defined. And if you replace the mass of the single oscillator by the reduced mass of the molecule, then the energy levels which you get, those are nothing but the same as those of a diatomic molecule. So this is a very important thing to note. So the vibrational energy levels of the molecule will be identical to the energy levels of the oscillator having reduced mass of the molecule. The bond length R of the vibrating molecule is equal to the length of the oscillator. So these are some of the things to note. Well, you can see a diagram now on the screen which shows the equivalence diatomic molecule to a harmonic oscillator, provided you replace the mass of the oscillator by the reduced mass of the diatomic molecule, 1 by mu equal to 1 by m1 plus 1 by m2. So this is shown pictorially at the beginning of the screen. And the harmonic oscillator now has quadratic potential, which is given by Vx equal to half kx square or equal to half m omega square x square, as we have already told you. So if the mean position of the oscillator is at x equal to 0. Now for a diatomic molecule with reduced mass mu and mean bond length r0, this potential has the form Vr equal to half k times r minus r0 square equal to half mu omega square times r minus r0 square. So you can check that Vr0 is equal to 0 for the resting molecule, because if the molecule, you see, actually R0 is the bond length, so the molecule vibrates around its bond length. Okay, so it is compressed or elongated around its bond length. So the resting position corresponds to R equal to R0 when V is equal to 0. The energy levels for molecular vibrations are denoted by the quantum number V instead of N. This is just conventional. Just when you come to diatomic molecules, molecular vibrations, then instead of writing N for the quantum number, you write V. So V is the vibrational quantum number of a molecule. And omega is 2 pi nu 0. And it is important to note that this is root of k by mu. Well, the mass of the oscillator is replaced by mu, the reduced mass of the molecule, and k now becomes the stretching, you see, stretching constant for a diatomic molecule, okay, or the bond stretching constant as it is sometimes called. Now you see there are some selection rules which we are not discussing, which restricts the transition in an oscillator by the selection rule, which is delta V equal to plus minus 1. That is, the electron can jump from V equal to 1 to V equal to 2 or 2 to 3, but it just cannot jump from 1 to 3. Okay, so this is governed by the selection rule, that is delta V should be plus minus 1. So let me just read out. The energy levels for molecular vibrations are found to be equally spaced for the first few values of n only, like harmonic oscillator. So the figure shows the potential energy curve as well as the energy levels for the molecule, and you find that the first few levels are more or less equally spaced, okay, as in the case of harmonic oscillator. But when you go higher up, then the energy levels become closer and closer, and ultimately you see they become very close together at a point when the molecule dissociates, okay, because if the vibration is too vigorous, then the molecule will not be able to stand that kind of vibration and it will dissociate, okay, and when it dissociates, the molecule no longer exists, and the vibrational energy levels also, you see, they no longer they do not exist anymore, okay. So because a molecule has got dissociation energy, so that is why you see the right hand portion of the curve is becomes a little different, okay. The lower part of the curve is parabolic, and there you have equally spaced energy levels, but because when the molecule tends to dissociate, the potential energy curve, you see, becomes different on the right hand side, and the energy levels also will become closer and closer. If the dissociation energy were infinity, then you would have a perfect parabolic potential and equally spaced energy level, but in nature, that in real life, that doesn't happen, because the molecule cannot stand vigorous vibrations, and it has to dissociate at some point. And the usual dissociation energy for a diatomic molecule is something like 4 to 5 electron volts. So now let me read out. The shape of the potential energy curve also deviates from its initial parabolic nature and becomes asymmetric, as I told you. Thus, the molecular vibrations are not exactly like a harmonic oscillator. The quadratic potential must be modified to include at least a few smaller terms of higher power in R minus R0. So you see, if you just say VR equal to half K R minus R0 square, then this corresponds to simple harmonic motion. But since the motion is anharmonic, okay, so you have to add a few terms of higher order, of higher degree of R minus R0. Okay, so we have added two terms, A R minus R0 to the whole cube plus B R minus R0 whole 4 to the power 4. So here A and B, these are constants. These constants are small compared to K, so that you see the dominant role is played by the first term of this potential, which corresponds to harmonic oscillations, and the other terms, you see, they are some kind of perturbations over the first term. So therefore these have to be kept small. So the values of A and B should be much smaller than the value of K. So the cubic term is needed for asymmetry of the potential energy curve, while it can be shown that the fourth power term reduces energy gaps. Well, this introduces asymmetry, the asymmetry in the potential curve, and this reduces the energy gap. The molecular vibrations, so let me read out. The molecular vibrations are anharmonic, which are best described by the Morse potential. Because you see, Morse potential is the standard way of describing a molecular vibration. Well, the form of the Morse potential is written here. It has an exponential function which can be expanded into terms containing quadratic, cubic, and fourth powers in R minus R0. The Morse potential for a diatomic molecule is what is written here, VR equal to dE 1 minus E exponential minus beta R minus R0, and then the whole square appears here, and where dE is the dissociation energy of the molecule. As I said, that all molecules must dissociate, and the dissociation energy for hydrogen molecule, for example, is something like 4.5 electron volts, and R0 is the bond length of the molecule. The bond length of the molecule is usually about more than 1 angstrom. It's usually about 1.5 angstrom or so. So these are the two important parameters. The one is the dissociation energy of the molecule which you are considering, and other is the bond length of the molecule which you are considering. So what is this constant beta? This is equal to K upon 2 dE, or which is equal to omega mu upon 2 dE, where dE is the dissociation energy and K is the stretching constant of the bond. Okay, so if you expand this, well, if you know the expansion of an exponential factor, then you can expand this and you can find that the Morse potential actually corresponds to the potential VR, which contains different powers of R minus R0 as shown on the screen. Now you can check a few things that you see. For the Morse potential, if you differentiate V and put it equal to 0, it gives R equal to R0. So this tells you that the potential energy minimum occurs at R0, which is the mean bond length of the molecule. Okay, so this shows that you are on the right track, that the Morse potential gives you minimum potential energy at R equal to R0. And then the second thing you can check is that V is equal to dE for R tending to infinity, and V equal to 0 for R equal to R0. Thus, the energy required to stretch the bond from R0 to infinity is dE, which is the dissociation energy of the molecule, or the depth of the potential minimum. So the parameter B contains the stretching constant K of the bond. Now then, the Morse potential is asymmetric, indicating that it is harder to compress the bond than to stretch it apart. The anharmonic oscillator described by Morse potential is referred to as the Morse oscillator. So all the diatomic molecules can be called Morse oscillators rather than simple harmonic oscillators. Then the energy levels for the anharmonic oscillator are obtained by solving one-dimensional Schrödinger equation for Morse potential. Well, the solution is complicated and rather approximate. Well, it will require a few pages if I want to come to this result, but here I'll just mention the result, which is important for you. You see, the result is the vibrational energy level equal to V. You see, if it were just a simple harmonic oscillator, the result would be V plus half H cross omega. But if you solve Schrödinger equation for Morse potential, you get the extra term, you see, which is V plus half whole square H cross omega square upon 4 dE, where dE is the dissociation constant. So you see, this changes the energy gap, right? Well, this term is important only for larger values of V, because the square appears here. So for larger and larger values of B, you see, this difference becomes more and more important. And since this appears with a negative sign, so as you go higher up, the energy levels get closer and closer for the molecule, and that is what we would expect. So this is the right description of the energy levels of a molecule. So you can observe here that the dissociation energy appears in the denominator. So if you consider theoretically, if you consider a molecule which has got very large dissociation energy, then this term becomes negligible, and the vibration would be more like simple harmonic. But in real life, that doesn't happen. This dissociation energy, as I said, is about 4 to 5 electron volts, and therefore this term becomes more and more important as we go to higher and higher levels of vibration. And then you see delta E, that is difference between any two consecutive energy levels. Well, that turns out to be, if you just find E V plus 1 and subtract EV from EV plus 1, then that is the delta E. That is the energy gap between any two successive levels for a Morse oscillator or for a diatomic molecule. The result you get is h nu 0 and minus V plus 1 h nu 0 squared upon 2 dE. So this means that if it were a simple harmonic oscillator, then the gap would always be h nu 0. But in the case of a Morse oscillator, the energy gap goes on decreasing and decreasing when you go to higher values of B. So this gives the right energy gaps. So let's do an example. The observed dissociation energy of the molecule H2, that is hydrogen molecule, is 4.5 eV. If the molecule behaved ideally like a harmonic oscillator with frequency nu 0 equal to 1.32 times 10 to the power 14 hertz, what would be its vibrational quantum number corresponding to this dissociation energy? Well, actually the hydrogen molecule is a Morse oscillator, but the question says that if it behaved ideally like a harmonic oscillator with the frequency which is given, then what would be its vibrational quantum number? See, corresponding to the energy 4.5 eV, which is the dissociation energy. Well, you can note one thing, that the frequency is 10 to the power 14 hertz. You see, there's so many vibrations, oscillations per second, you see, which means that you see billions of oscillations per second. Well, let me now discuss the solution of this problem. Now, if the hydrogen molecule behaved exactly like a harmonic oscillator, the vibrational quantum number corresponding to the observed dissociation energy can be estimated by setting the vibrational energy equal to 4.5 eV, which is equal to so many joules. Because you are doing the calculation in MKS units, so you have always have to convert the unit electron volt into the unit joules. Okay, that's the MKS unit for energy. So the nu 0 is given. You see, that is the oscillator frequency. So that is 1.32 10 to the power 14 hertz for the molecule hydrogen. So what we do is that the simple harmonic oscillator energy levels, these are V plus half h nu 0. So on the right hand side you have written V plus half h nu 0. And on the left hand side you want this energy to be the dissociation energy of the hydrogen molecule, so which is 4.5 electron volts, and you have changed it to joules, so it's 4.5 times 1.6 times 10 to the power 19 joules. So this is on the left hand side. So you see, you have to solve for V from this equation. At what value of V the energy of a simple harmonic oscillator would be equal to the dissociation energy for hydrogen? This was the question. So if you solve this equation, solving this equation for the nearest integral value of V, we get nu equal to 8. If you solve this, then you'll get some fractional value, but you have to take the nearest value, nearest integral value of V, because this is a vibrational state, so it has an integral value. So there can be small error. You see, when you get the result may not be exactly 8, it may be 8 point something, but you have to take 8. So, I mean, if the hydrogen molecule behaved exactly like a harmonic oscillator, then you would only have 8 energy levels before you come to the dissociation energy of the hydrogen molecule, which is 4.5 eV.
Let us now summarize what we have learned from this lecture. The Schrödinger equation is solved for harmonic oscillator to obtain the energy levels and wave functions. Then, lowest energy level is the 0-point energy, which does not have a classical analog. Then, the probability curve fluctuates for higher values of the quantum number n, but its average is consistent with classical behavior. Then, there is always a probability of observing the oscillator beyond its classical amplitude. Well, this is a very important point. Then, energy levels of a vibrating molecule are identical to those of an oscillator having reduced mass of the molecule. And finally, vibration of a molecule in real life is anharmonic, and its energy levels can be obtained by solving Schrödinger equation for what is known as the Morse potential. Thank you.